Okay, this example is very similar to the last example. Notice the graph, though, in purple, that we're still calling it y equals f of x, but the graph in purple is continuous. And what I mean by that is you could draw it from this weird-looking open point with, all the way from here. You could draw it without lifting your pen or pencil. So that's what I mean by continuous. So it's still going to be, this graph still represents a set of ordered pairs, and it will be a function because it passes the vertical line test. It still represents a set of ordered pairs that represents, in fact, a function, except there's an infinite number of ordered pairs that goes with this graph. So the idea is any point on the graph is an ordered pair that makes up the function. And there's an infinite number of them because between any 2 points, you can fit another point. And you take all that infinite number of points and smush them together in kind of linear fashion, like so, up and then down and then a line up, and you get the function. Okay, so it's a function comprised of an infinite number of ordered pairs. So in part A, we're going to find f of 1. Remember, the number that goes right here is your input. It's what you're plugging in for x. X always stands for an input value, right? A generic input value. So what's f of 1? How do you find f of 1? Well, you go on the x-axis or the horizontal axis. It doesn't have to be called x. You go to a distance of 1 or from 0. So you go over to 1 right here. And then you want to find the output value that goes with an input value of 1. So go up to the graph in this case. 1, 2, 3, 4, 5. So this output value of 5, in other words, the point 1, 5 is on the graph. So for an input value or a first coordinate value of 1, you get an output value or a second coordinate value of 5. In other words, f of 1 is equal to 5. And that's part A. So the domain, okay, remember, domain values appear on the horizontal axis, the x-axis in this case. And so this graph appears all the way from, it appears as though it goes from x equals -3, well, maybe not quite -3 because of that open circle right there. So it goes all the way from maybe almost this point, horizontally, all the way from this point, which is at -3, all the way to the right, maybe to this point, which is at, I think, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so the low value on the domain, well, we haven't talked about the open circle yet, but it gets close at least to -3, as you'll see. And then a solid circle here, so looks like it gets all the way horizontally, x value-wise, looks like it goes all the way from -3 to 7. Okay, so we're going to write the domain using inequalities because we can't go by ones in this case. It contains all the x values in between -3 and -2, as well as -2. And it contains all the values in between -2 and -1. So you can't just list the domain values like we did in the last example. We have to use inequalities here. So what I'm going to do is I know the first value in the domain is almost -3. And the last value is 7. So I'm going to put x in between -3. So x always stands for the domain values. Well, not always, but in this case it does. And I'm going to use less than inequalities. In this case, a strict less than. And over here, a less than or equal to. Okay, so it's time to talk about the open circle. This open circle means that this point is not included in the graph. You can get as close as you like to this point from this direction on the graph, but you won't ever actually get to that point. That point, what's that point? That point is -1, 2, -3, 1, 2, -3. So you don't quite get to -3, -3 on this graph, but you get as close as you like. So horizontally speaking, then, x never quite gets to this value. So we'll use a strict less than right here. So we're going to say -3 is less than x. And then if you look horizontally and go all the way to the right until you're just below this point, then it does look like x reaches that point because it's a closed circle. So x does reach 7. So you use a less than or equal to. X is less than or equal to 7. The domain then is -3 is less than x, which is less than or equal to 7. In other words, x is between -3 and 7, not including -3, including 7. Now, we use more notation than just inequality notation. We use what's called set builder notation to express this domain. So I'll use D for domain, and I'm going to throw in a couple of symbols. I'm going to use the curly bracket you're familiar with. I'm going to throw in another x, and then a vertical bar, and then I'm going to end, at the very end, I'm going to put on another curly bracket. This is called set builder notation. And the way you read it is, okay, you would read this curly bracket or translate it as the phrase, the set. This vertical bar means such that. It translates directly to the phrase such that. So this notation, this jargon means the set of, okay, well, this guy translates to just x. So I'm going to write it like this. The set of all x, you do have to include the of all, and then the vertical bar such that, and then just the inequality, such that -3 is less than x, which is less than or equal to 7. So this weird-looking set builder notation means the set of all x such that x is between -3 and 7, not including -3, including 7. That's called set builder notation, and you do have to know that notation for the exam. Next, for part C, we want to find any x values, in other words, input values, such that f of the x value equals 3. Oh, okay, so this is an output value. Output values, or range values, appear on the vertical axis. They're height values. Think of it that way. So go to a height of 3 on the y-axis, the vertical axis. Oh, and it looks like there's a point in the graph right there as well. Go to a height of 3. I don't think it'll do any good to go to the left. You won't get to the graph if you go to the left. But if you go to the right at that height of 3, you're going to intersect the graph not at one more point, but at 2 more points. So 2 points here and here. Okay, so we want to list all the x values, or first coordinate values, or input values that have y values, or second coordinate values, or output values of 3. Okay, so what are the corresponding input values that go with these points that are at a height of 3? This first one's got to be x equals 0. So x equals 0 would work. What else? This value right here, I don't know. I'm just going to guess. It's not 2.5, 2.2, 2.3. Anything in there would work. And this one we'll have to guess as well. Maybe 1, 2, 3. We're going by ones here, by the way. 1, 2, 3, 4, 5. Maybe 5.5. As long as you're close, that answer will be acceptable. That's part C. Now, part D, the range. Okay, for the range, you think, how low does the graph get? How high does it get? And because it's continuous, it will hit all the values in between. So how low does it get almost to? It almost gets to a height of -3. That's what this was supposed to say right here, -3. This second coordinate was supposed to be -3. And so it goes, that's the low value, or it almost gets there, it never quite gets there because of the open circle. And we're talking about the second coordinate. They happen to be the same here. The second coordinate, the height value is at -3. Okay, and then how high does it get? It gets up here to 1, 2, 3, 4, 5, 6. This would be the high value. So from -3 to 6. Those are the values that the outputs will lie between. Now the outputs we're going to call, whatever letter we denote the vertical axis by, we're gonna say y here denotes those outputs. And we're going to use inequalities once again. You never quite get y, the height of this graph never quite gets to -3 right there. So strict inequality right there. And then y does get to a height that's 6, again, because that's a closed circle versus over here, that's an open circle. So less than or equal to. And again, we're going to use the set builder notation. So we'll use R for range, throw in an extra curly bracket, an extra y value, a vertical bar, and another curly bracket. And you read that, this is once again, it's set builder notation. You read this as the range is the set of all y values such that, the vertical bar means such that, y is between -3 and 6, not including -3, including 6. And that's it.